All right, imagine trying to solve a massive, mind-bending puzzle, only to realize that the very rules defining the pieces are completely wrong. Well, that's exactly what we're jumping into today with this explainer, because we're looking at a massive conceptual shift that is literally rewriting the foundation of artificial intelligence. We're talking about a fundamental flaw, one that has secretly haunted how we train AI for decades. And fixing it, it changes pretty much everything we know about how machine learning actually works. Seriously, just stop and think about this for a second. If I handed you a hard drive, completely filled with a billion truly random numbers, how much would you actually learn from it? Like, what knowledge could you possibly extract from pure, unfiltered noise? And here is the absolutely incredible paradox. According to classical mathematics, and specifically Claude Shannon's foundational theory of entropy, that pure random noise is technically the most information-rich thing I could possibly give you. The math says it's maximal. Why? Because every single number is completely unpredictable, meaning every new number is a totally new piece of data. But practically speaking, as a real living learner, you'd extract absolutely nothing. Zero. Zip. Because pure randomness is just chaos. There's no underlying pattern to grab onto, no structure to generalize from, and absolutely nothing that actually makes you smarter about how the world works. So think about true randomness on one hand, just pure unadulterated chaos. And on the other hand, you have a sequence generated by a complex deterministic math equation. Now, Claude Shannon was an absolute genius, but he made one fatal assumption in his theory. He assumed the observer of this data is infinitely powerful, right? To a godlike entity that can instantly see the mathematical formula behind that generated sequence, it contains very low information. But to a computationally bounded AI model, well, both of these sequences just look like perfectly random noise. Neither can be learned from. Shannon's math works beautifully for gods, but AI models, just like us, have hard physical limits on their compute. Okay, so how do we actually fix this paradox? Enter a revolutionary new metric from researchers at Carnegie Mellon and NYU that completely redefines the value of data based on those exact finite limits. They call it epiplexity. Epiplexity measures the structural information that a computationally bounded observer can actually learn from data. So it's no longer about this theoretical maximum of information just floating around in the universe. It's about what a real learner with a very real limited compute budget can pull out and actually use to get smarter. Just look at the visual representation here. Those intricate swirling structures and architectural shapes being pulled right out of the chaos. AI doesn't just passively pattern match its way through an ocean of data. It can't. It has to use its finite, precious compute budget to actively carve out and build an intricate understanding from all that surrounding noise. It literally has to spend computational energy to find that hidden architecture. So, consider where the real value of data actually lies when you finally factor in that compute budget. Pure random noise? High entropy, sure, but incredibly low epiplexity because there's zero underlying structure to learn. Then, think about a simple repeating pattern, like ABAB. Low entropy and low epiplexity. You predict it instantly, so no meaningful learning happens. But then, you have structured complexity. Think human language, highly technical science papers, or a game of chess. This right here is the ultimate goldmine for training data. It sits perfectly in the sweet spot, hard enough to require serious computational effort to figure out, but structured enough that learning is actually possible. Which brings us to a really crucial point. For years, the standard metric for evaluating AI training data has been this thing called perplexity. And perplexity is essentially just a proxy for Shannon entropy. It basically measures how surprising or unpredictable data is to a model. But if entropy is the wrong measure for a bounded learner with finite resources, it means we have literally been judging and selecting our AI training data using the wrong ruler entirely. We've been optimizing for surprise instead of learnable structure. Now, epiplexity doesn't just give us a cool new vocabulary word to throw around. It actually resolves three massive, seemingly impossible paradoxes in AI right now: the synthetic data illusion, the curriculum ordering mystery, and the emergent reasoning myth. Let's break these down. Let's tackle the first one. Classical information theory strictly states that you cannot create new information from purely deterministic operations. So, how on earth does AlphaZero, an AI playing chess against itself in a strictly deterministic, closed loop, manage to achieve superhuman intelligence? Or, for that matter, why does synthetic data make modern language models so much better? Well, epiplexity answers this perfectly. Deterministic compute doesn't invent new, raw information out of thin air. Instead, it brilliantly converts latent, hidden structure into accessible, highly learnable epiplexity. When AlphaZero plays a million games against itself, it's essentially calculating the hidden, complex rules of chess strategy and surfacing them into a format it can digest. It makes the underlying structure visible. It turns raw computational efforts into highly valuable, structured training data. Okay, on to the second paradox. Classical theory says the order you shuffle your data in shouldn't matter at all. Data is data, right? But anyone who actually trains AI knows that curriculum ordering matters immensely. The researchers ran this beautiful experiment where they fed an AI a sequence that was much, much harder to process. They asked it to predict chess moves backwards from the final board state. Because this unnatural direction taxes the model's compute so heavily, it struggles, but the epiplexity shoots way up. This intense computational pressure literally forced the AI to construct deeper, more robust internal circuits just to handle the backwards logic. And the result? The model became far smarter and performed incredibly well on novel, out-of-distribution chess problems it had never even seen before. Harder, carefully ordered tasks force deeper internal programming. And that brings us to the third paradox, the persistent, super dismissive myth that AI is just a giant statistical next token predictor that simply memorizes patterns and regurgitates them like a stochastic parrot. The framework of epiplexity completely dismantles that myth. Under the crushing pressure of a finite compute budget, a model cannot possibly just memorize everything in its massive training sets. It is physically impossible. In order to minimize its error rate without running out of memory, the model is forced to physically compute new internal algorithms, subroutines, and generalized shortcuts into existence. It isn't just matching surface-level patterns, it is dynamically computing genuine reasoning and understanding into existence simply because that is the most mathematically efficient way to survive its compute limits. So let's look at the practical implications of this massive shift. What does this mean for how we actually build AI going forward? Well, first, we have to focus intensely on maximizing learnable structure in our training data rather than just dumping in raw, chaotic complexity. Second, it means we have to prioritize highly structured data like code, mathematics, and complex language over simple images for reasoning tasks, because language inherently requires more internal programming to model. It has higher epiplexity. Third, we now understand that synthetic data is definitely not cheating. Generating high-quality synthetic code is a deliberate engineering tactic to create learnable structure. And finally, curriculum design, like using step-by-step reasoning chains, is no longer just an art, it is a hard science that physically alters what structure the AI is capable of extracting. And honestly, this fundamental shift perfectly explains why AI scaling laws work so well. You always hear that throwing more compute and data at a model predictably makes it smarter, but we lacked a clean physical theory for exactly why that happens. Well, here it is. More compute doesn't just make things faster, it literally increases what counts as information. Throwing more compute at a model allows it to unlock and extract deeply buried structures in the data that were previously completely invisible to it. The data itself didn't change. The model's capacity to extract epiplexity did.
Which brings us to a profound final thought to wrap this explainer up. For this whole time, we've been asking what information is to an artificial intelligence. But what is information to a computationally bounded mind like yours? Think about how you learn. A book that is entirely too easy gives you nothing. A book that is totally incomprehensible, written in a language you don't even speak, also gives you nothing. But the hardest book you can just barely understand. That is your personal point of maximum epiplexity. That is where true intellectual growth actually happens. This isn't just a theory of machine data, it's a fundamental theory of growth. So, what highly structured challenge are you going to use your finite compute budget to extract today?